Hey guys, so this is going to be a new mini series on the channel on image charges. Now, image charges are a really interesting and weird trick to solve for electric fields without really solving for electric fields. It's really interesting, it's really weird, and we're going to be doing a series of videos covering image charges, their motivation, how to use image charges, and a bunch of questions on them too. This first video on this series isn't going to cover image charges at all directly. It's going to cover rather the motivation behind image charges, why the trick works, what is behind image charges, and what lets us use them. And then in further videos, we'll actually use image charges and look at how to solve for electric fields using them. Now, this first video, I've written these points here for what we're going to be doing in the video. We're going to be discussing Laplace's equation, where it comes from, what it is, and what its relevance is to solving for electric fields. We're going to be learning how to solve it, sort of. We're not. This isn't a math lecture series. We're not going to be really learning how to analytically solve the Laplace equation. We're going to be learning rather some ways we can manipulate it and you bring it into something we can use for image charges. We're going to be discussing properties of the equation. That's going to be necessary to prove the uniqueness theorems, which are extremely important for image charges and is the whole reason we're studying the Laplace's equation. So without further ado, let's just get into firstly why we're even considering the Laplace's equation. Now, if you're studying image charges, so far you've probably studied these things already, which is solving for electric fields in two different ways. Now, solving for electric fields is sort of the most fundamental thing we do in classical electrostatics. Every chapter you're going to study in electrostatics is going to be talking about computing electric fields, right? And we've learned you've probably, at least I hope you've learned two ways of doing this so far before you tackle image charges. One is just the actual normal mundane integrals for the electric field, because where this integral comes from is the electric field is sort of defined as if you have a point charge, the this is what your electric field for the point charge is a distance r away, and you can generalize that to an infinitesimal charge and then integrate over to find the whole electric field for any charge distribution. This is a general charge distribution. Integration will theoretically give you the answer for any electrical field. The problem is this integral can be really annoying to solve. It can be a real pain to solve. The reason it can be a pain to solve is because of this thing here, the unit radial vector. The reason this is a issue is because let's say you have some charge distribution. This is our little charge distribution, and you want to look at the electric field at a point some distance away. You can't directly add up the contributions from each infinitesimal charge on this distribution. The reason is because they will be vectors pointing in different directions, and only vector addition can get you the actual electric field and its direction. That is why we often don't use this integral directly. Instead, we look at another quantity. That quantity is called electric potential. The electric potential is not a vector quantity, it's a scalar field. It being a scalar field means we don't have to do vector addition, rather, we can just add these infinitesimal contributions up in an integral, and you don't have to do vector addition at all. That's why the electric potential is useful to us in the first place. And then after you find the electric potential at a distance from a charge distribution, you can directly, oh, I've missed a minus sign here. This should be minus the gradient of V. You can directly convert this scalar field, the electric potential, into the electric field, which is what we're looking for, just by taking the gradient of this potential field. And these are two ways to solve for the electric field. The problem comes is that with a lot of situations, and particularly with conductors, which is what we're going to be talking about a lot in the series, um, integration and solving these types of integrals, even with this trick with the electric potential, can be really hard and can often be basically impossible or literally impossible. So we need to expand our tool set on how to solve for electric fields around especially conductors and also other setups. And to do that, we need a new sort of trick in our bag of tricks to find these electric fields. And that's where Laplace's equation actually comes in. because through Laplace's equation, we can prove something called a uniqueness theorem, and we'll prove multiple uniqueness theorems. And these uniqueness theorems can let us directly find electric fields without doing any integrals using something called image charges, which we'll cover later. Now, what is Laplace's equation, right? Where does it come from? Like, I've written this equation down over here, but what even is this? What is this double triangle square thing? That's what we'll cover now. So, for the Laplace's equation, to get the Laplace's equation, you really need two other equations, which is sort of the divergence, Maxwell's law for the divergence of the electric field. Nabla dot E is equals to the charge density over epsilon naught. This is the charge density in a particular point in space we're looking at. And you need the other equation, which is just converting a scalar potential field into an electric field, which is the gradient of a potential field, or the minus gradient. I keep forgetting the minus, I don't know why. The minus gradient of a potential field gives you the electric field. Now you can take this definition of the electric field and you can plug it in right over here. And what that gives you is it gives you a term where we have nabla dotted with a gradient of the electric potential, and we have to put a minus sign here because of this minus sign, and this equals the charge density divided by epsilon naught. Now put your focus your attention on just this part of this expression, the nabla dot some gradient, right? This can be written in another way. This is just a short form of writing this. Instead of writing this whole thing with nabla dotted with another gradient, we just write simply nabla squared of a scalar field. We put the minus sign on the other side, equals minus rho over epsilon naught. Now, what actually is this whole expression, this nabla dotted with a gradient expression? What does it, what can we evaluate it out to in Cartesian coordinates to kind of get a better gist of what we're looking at, right? Well, think about the gradient of a scalar field is. If we write this expression, this simply means you have the partial derivative of the scalar field with respect to x in the x hat direction plus the same thing in the y hat direction but with the partial derivative of y, and the same concept goes on for the z direction, right? And then we want to dot product this with nabla. This whole expression over here, we're gonna do a dot product with the gradient vector, right? Well, what is the definition of this nabla? Nabla is simply dx in the x hat direction plus dy in the y hat direction with partial derivatives plus dz in the z hat direction with partial derivatives. And when you dot this expression with this, I think you'll be able to see that you get that nabla squared of v is simply going to be d square v over dx squared plus the second derivative of v with respect to y, and then the second derivative with respect to z. This is what we get for this whole expression nabla squared of v. And that is what we have in the Laplace's equation. Now, you might notice that this isn't really the Laplace's equation. This is equal to something. The Laplace equation I told you was equal to 0. Hey, start recording. The reason for that is that for the whole analysis of image charges and using the Laplace's equation, this isn't the Laplace equation by the way, this is called the Poisson equation. We're going to be concentrating on regions of space with zero charge density, where this rho is 0. That doesn't mean that there's no charge anywhere. What I mean by that is, for example, let's say you have a conductor, some sort of spherical conductor, or let's say you have a bunch of conductors. Let's make a triangle conductor and a square conductor. Let's say these all are conductors. They have some charge on their surface, distributed on their surface, and they produce electric fields, right? If you look at the surface of this conductor, yeah, there's going to be a charge density here, and we'll need to use if we want to analyze this point in space, we would have to use the Poisson equation, which is where we have this equality to the charge density over epsilon naught. But look at every region of space. Look at this point, for example. Let's call this point P. This point in space, there's zero charge density here because it's far away from the conductors. That doesn't mean there's no electric field here, because these conductors will cause some sort of electric field here. And at this region of space, we will simply have the equation that the nabla squared, I'm going to keep calling it, of the potential field is equal to 0. And you might say, now, how does this make sense? Because let's say you remove all these conductors and you just have empty space, right? Wouldn't this equation also apply here? And why can it apply in this place? Why can there be a solution to this equation here? And we would have to have a completely different solution for the potential in empty space, right? Well, the thing is, this equation is completely dependent on something which we're going to discuss shortly, or maybe in another video on this series, called boundary conditions. The Laplace equation is useless without boundary conditions. Boundary conditions are being applied onto this equation are what lets us get the exact potential field that we want. What is a boundary condition? A boundary condition is you specify, okay, so we're looking at a region of space where the nabla squared of our potential field is 0, right? And that could be satisfied by just empty space where there's no charge anywhere, and then the potential field is 0 everywhere. It could be specified by these conductors causing a potential at point P, right? And the way we differentiate between this scenario where we have empty space, and a scenario like this where we do have charge somewhere, we have a different charge distribution, is I can sort of input into the equation the fact that each of these conductors will have some potential on them. It could be V1, V2, let's say V3. Conductors are equal potentials, which we'll talk about later. That means the potential at every point on the surface of the conductor is the same, just constant V2, V1, V3. And we can also say that infinitely far away, if you go infinitely far away from this whole setup, then your potential should just go to 0. So this V inside this equation, we're going to sort of specify or constrain on the equation that it should be V1 on this region, for example, if we're given that, V2 on this region, for example, and V3 on this equation, and then 0 infinitely far away. And that sort of constrains the solutions to this equation so that we can actually find V. How are we going to find V? I'm not going to solve this. Okay, wait, look at this equation. We are not going to solve this second order differential equation analytically. This isn't a math lecture, and frankly, I don't know how to solve this equation analytically. I'm a physics student myself. But this equation, even though it looks really daunting, like looking at this differential equation, it's like, how do you solve this even with putting in boundary conditions? There's certain tricks of the trade, which, aka uniqueness theorems, which we're going to talk about now, which let us sort of use tricks to find solutions to V without solving analytically. And that's what image charges are. And that's why now we're going to move into proving the uniqueness theorems through looking at certain properties of this equation, the Laplace equation. And I know I said that I'm going to prove the uniqueness theorems and these properties in this video. I said that we're going to do this and then this video. I think now I'm just going to break these two things up. We've covered the Laplace's equation, where it comes from, why we need to solve it, and we've talked a bit about why it's hard to solve it. So now next video in this series, I'm going to talk about properties of the Laplace's equation, which let us derive which let us prove some uniqueness theorems. And then after we prove the uniqueness theorems, we can jump right into image charges and how they work and how to use them to solve for electric fields. Thank you so much for watching this video, and watch the next one. And yeah, bye.